2, Section 5, which is the fundamental theorem of algebra.
Oh boy.
Yeah, sounds real fancy, don't it? It's really not that bad. It says, you know that an nth degree polynomial can have at most n real zeros. Okay, so what are they saying? They're saying, all right, well, we talked about if I had a fifth degree polynomial, what is the maximum number of x-intercepts? 5. That's what they're saying there. You know an nth degree polynomial can have at most n real zeros. But in the complex number system, this statement can be improved. That is, in the complex number system, every nth degree polynomial has precisely n zeros. This is an important result that was derived from the fundamental theorem of algebra, which is first proved by the German mathematician Carl Friedrich Gauss. There's his birth years and death year. Nice. Okay, so if f of x is a polynomial of degree n, where n is greater than 0, then f must have at least one 0 in the complex number system. That is the fundamental theorem of algebra. But what we're going to use that's a little bit more impressive is the linear factorization theorem that says if f of x is a polynomial of degree n, then f has precisely n linear factors. So, again, the word that I like to use is roots, because in my head, x-intercepts and zeros is where it crosses the x-axis. But roots can be both complex, which means imaginary, and real. So if I have an 8th degree polynomial, there are 8 roots every time, real or imaginary. It always matches. If I have a 16th degree, then I'm going to find 16 roots. So where before we could say there was at least this many x-intercepts, we could say a 5th degree had at most 5 x-intercepts. Now then a 5th degree is going to have 5 roots, or it's going to have 5 factors every time. Work some out for us here. So if I have a first degree polynomial, f of x equals x minus 2, then it has exactly one root. It has exactly 1 0. So remember, we set y equal to 0, and we solve. So we would get x equals 2 as my only 0. So first degree had 1 root. Now here's the second degree. So this second degree polynomial, x squared minus 6x plus 9, they factored it to be x minus 3 times x minus 3. So these are the 2 factors, which means it has 2 roots, at 3 and at 3. Or we could say the x-intercept of 3 has a multiplicity of 2, because it happened twice. Again, called a repeated 0, because that root happened multiple times. Next, we have a 3rd degree polynomial. Okay, so you can see if I started here, x cubed plus 4x, I would tell you 3 sections ago, GCF. There's a GCF of x. So we're going to factor the x out. So it's going to be x squared plus 4. Now this wouldn't factor. And so normally we would be stuck here. Alright? But now because we can work in the imaginary number system, then we can solve this. We could set x squared plus 4 equal to 0. X squared equals negative 4. Then we take a square root. We're going to get x equals plus or minus the square root of negative 4, which is plus or minus 2i. The square root of 4 is 2. We bring out the negative as an I. So you can see there are the 2 factors there. And so again, the 3 roots are 0, 2i, and negative 2i. So we're fixing to start talking about, well, how many real roots does it have? How many complex roots does it have? Or imaginary roots? This one has 1 real root because it doesn't have an I. 0 is a real root. These 2 are imaginary roots. So right now when we graph in the xy coordinate plane, we are not going to see imaginary roots show up anywhere. We will just see them, the 1 regular root, which was x equals 0. Next, here's a 5th degree polynomial. So same idea. We know we're going to find 5 roots. So GCF, that has an x squared, x cubed as a GCF. So I can factor the x cubed out. That leaves me with x squared plus 9. Then same thing, we can set this equal to 0 and solve. So we find roots to be at 3i and negative 3i. And because I'm setting x to the third equal to 0, then that really means I've got x times x times x times x squared plus 9. So we could set x equal to 0, x equal to 0, x equal to 0. So an x to the third is going to give 3 roots from it. So 0 is happening 3 times. And then you have 3i and negative 3i. Okay, so it tells me here, determine the number of zeros of the polynomial function f of x equals x to the fourth minus 1. So it doesn't ask me to find out what they are, just how many are there. How many zeros are there? 4. 4. 4. It's 4. How do you know it's 4? Because it's degree 4. Now we could factor this if we wanted to. That's the difference of perfect squares. Yeah? X to the fourth is a perfect square. 1 is a perfect square. And now this is a difference of perfect squares. So that's x plus 1 times x minus 1. And then I'm going to set this one equal to 0 because it's going to give me imaginary roots. So my roots are negative 1, 1, I, and negative I. Not only can I tell you there are 4 roots, I can identify what the 4 roots are. So we don't have to do that yet, but that's what we're fixing to be doing. So I thought I might as well do it there. But let's just repeat it here. Remember that n zeros of a polynomial function can be real or imaginary, and they can be repeated. So we're fixing to work examples 2 and 3, which are just several different cases of this. It tells me to confirm that the third degree polynomial x to the third plus 4x has exactly 3 zeros, and it tells me what they are. 0, 2i, and negative 2i. So if I had to find the zeros here, I'm always looking, is there a GCF? Yes, there is. They have an x in common, so I'm going to factor the x out. So now I've got x squared plus 4. And again, when we're looking for zeros, looking for roots, that means the y value is equal to 0. So I can change f of x to be 0 there. Now, 2 things multiply to be 0. That means either the first thing is 0 or the second thing is 0. This one's already solved for us, so we have a root at 0. Then solve the other side. X squared equals negative 4. Square root, square root. Whenever I choose to take a square root, I always account for the positive and negative possibilities. We bring out the negative as an I. Then the square root of 4 is 2. So I have 0, positive 2i, and negative 2i, which is the 3 roots that I expected. Write it as a product of linear factors. That really means factor this. They want me to factor it, and then they want me to list all of the zeros, which I call roots. Okay. So, if I had to factor this, number 1, is there a GCF? No. Okay, can this factor some kind of special case? Is it a difference of squares, difference of cubes? No. Could I factor by grouping? Are there 4 terms or 6 terms? No. So none of my factoring methods are going to work. So I'm going to have to guess some possible factors using synthetic division. So again, I can narrow down what I want to guess. What are the real roots or the possible rational roots here? So I'm going to list the factors of 8, which are 1, 2, 4, and 8, over the factors of 1. Well, okay. So I've got 8 things to choose. Right? 1, 2, 4, and 8, or negative 1, negative 2, negative 4, negative 8. I would always start with 1. Okay? Also, make sure when we're writing out our coefficients, there is no x to the 4th term. So I have to make sure I have a placeholder. So I have x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, constant. Bring down the 1. 1 times 1. Again, I can't talk and do this, sorry. I mean, I can try, but I don't know what it is. I guess I'm kind of brain blocked. So 1 worked. So that means what? That means I found my first 0. It's at 1. Which means x minus 1 is a factor. And then what's left are my other factors. So this is my constant, x to the 1st, x to the 2nd, x to the 3rd, x to the 4th. So now I have 1x to the 4th plus 1x to the 3rd plus 2x to the 2nd plus 4x to the 1st minus 8. So now I would want to go through the whole process again. Can I factor this? Is there a GCF? Can I factor by grouping? Well, no, it's still 5 terms. Grouping's not going to work. GCF's not going to work. So I've got to do synthetic again. So I'm going to try 1 again. But now then my coefficients are given here by the new depressed polynomial. So I have 1, 1, 2, 4, negative 8. Bring down the 1. So 1 worked again. So that means I have another 0 up here. I have 1 happening again. So now factored, I have x minus 1 times x minus 1. So we can write that as x minus 1 squared times, and then what do I have left here? This is my constant, x to the 1st, x to the 2nd, x to the 3rd. So I have 1x to the 3rd plus 2x squared plus 4x plus 8. And sorry, I know it gets a little sloppy when I just do it on the iPad, but I got to record it. I get so many people out. I got no other option. Okay, now look at what is in parentheses, my new depressed polynomial. It's 4 terms, so I want to try to factor by grouping. Okay, when I look at that, I know grouping is going to work just by looking, because I go from 1 to 2 and then 4 to 8. So that means the second one has just been multiplied by 4, right, of the first group. So I'm going to group those last 2 together. So now then, again, this x minus 1 squared is going to stay out here. Now I'm going to group. So my GCF is x squared. That's going to leave me with x plus 2. Then my GCF is going to be positive 4. That's going to leave me with x plus 2. Which means in blue, that factors to be what's in front of the parentheses times the matching parentheses. And then I have what was listed in front to start with. Now, can I factor this again? No, that's a sum of squares. If it was a difference of squares, I could factor it. But I know this is going to give me imaginary roots. And then here, I can set that equal to 0, and I've already found my two roots here, right? It was 1 and 1 again. Okay? So now then I need to find my other roots by solving here. But the first part of the question, write the factored form. That is the factored form. X minus 1 squared times x squared plus 4 times x plus 2. So now I'm going to find the roots from these two. So I'm going to set them equal to 0. So I'm looking, where does x plus 4 equal 0? And where does x plus 2 equal 0? Okay, well this one's easier to solve, so I'm going to do it. Negative 2 is going to be a root. And then over here, x squared equals negative 4. Square root. X equals plus or minus. Negative comes out as an I. Square root of 4 is 2. So now I have found all 5 roots. I have 1, 2i, negative 2i, and negative 2. Those are my 5 roots for my 5th degree polynomial. Okay, so hopefully you factor that as a difference of squares. So that would give you x squared and x squared, 16 and 16. Then alternate the signs, plus and minus. Then what's the next thing you need to do? Right here we have another difference of squares. So I can factor this to be x plus 4 times x minus 4. The first parentheses is a sum of squares, so it will not factor. It's going to give me imaginary roots. So now 3 things multiply to be 0. So either the first thing is 0, the second one is 0, or the third one is 0. So I'm going to get negative 4 as a root, positive 4 as a root. And then right here I've got x squared equals negative 16, which says x is going to equal plus or minus 4i. Those are my other 2 roots. So I have positive 4i, negative 4i, negative 4, and positive 4. So again, right here is my factored form. And then right here are my roots. Okay, so it tells me here, find a 4th degree polynomial with real coefficients. So it has to be a real coefficient polynomial. And it has roots at negative 1, at negative 1, and 3i. Okay, so we know it's 4th degree, so how many roots does it have to have total? 4. How many does it give me? 3 of them. I know negative 1 is a root, I know negative 1 is a root, and I know 3i is a root. But because it's a real coefficient polynomial, then if 3i is a root, then negative 3i must also be a root. So that is my 4th root that they don't state. So they're going to make sure you know that rule we just went over, because they're not going to tell you the other imaginary root. You've got to know it's got to be the conjugate. So we've done problems like this already. This is where we're working backwards. I'm given the roots. I want to get the polynomial in the end. So I'm going to work this backwards. So that means x plus 1 has to be a factor. X plus 1 has to be a factor. X minus 3i is a factor. X plus 3i is a factor. Remember how we're unsolving them. Setting them back equal to 0. Now then we want to multiply all of these together. X plus 1 times x plus 1 times x minus 3i times x plus 3i. So whenever you do this, I would always make sure when I distribute to distribute the conjugates. Like, make sure you do those together because they're going to make the imaginary parts go away. So like, if it was a 5th degree polynomial, then I don't want you to do, so just pretend like there's a 5th one out here. I don't want you to do these and then do these and then leave an imaginary one left undone. Always make sure you distribute the imaginary one by the other imaginary one, by its conjugate. Okay? So let's just start over there. So that's going to give me x squared. Again, when I distribute a conjugate, the outside and insides cancel. So that's going to leave me with negative 9i squared for the last ones. And then over here, that's going to be x squared plus 1x plus 1x, which is going to be positive 2x. And then 1 times 1 is 1. Is everybody okay with me skipping the outside, inside, and combining them? Okay. Just makes one fewer step. Now I need to fix this I squared. So I squared is negative 1. So negative 9 times negative 1 is going to be positive 9. And now I'll notice the imaginary units are gone, which means I'm going to have a real numbered coefficient polynomial. But I have to distribute again. So that's going to be x to the 4th plus 9x squared plus 2x cubed plus 18x plus x squared plus 9. Then group my like terms together. So I've got an x to the 4th plus 2x cubed plus 10x squared plus 18x plus 9. And again, since this is my polynomial, I'm going to say f of x equals this. Okay, so let's start here. Am I ready to go over this? Am I good? The roots are at 2, negative 2, 7i, and we know negative 7i must also be a root because it's real coefficients. So the conjugate must also be a root. Now then, we are working backwards. So write these as factors. So I have x minus 2 times x plus 2 times x minus 7i times x plus 7i. And I'm going to make sure I distribute the conjugates. This time they're all conjugates. Nice. So that's going to be x squared minus 49i squared. And then when I distribute over here, again, conjugates, so I'm going to have x squared minus 4. I'm going to fix I squared is the same thing as negative 1. So negative 49 times negative 1 is positive 49. And then distribute here. X squared times x squared is x to the 4th. That's going to be a positive 49x squared. That's a negative 4x squared. And that's going to be negative 196. You're going to do that in your head, right? And so when I combine my like terms, that's going to be x to the 4th plus 45x squared minus 196. That's correct. Find a cubic polynomial f that has real coefficients. So again, that's what we talked about yesterday. Real coefficient polynomial. Its x-intercepts are at 2 and at 1 minus I. But then they have some more information for us here. They tell us f of 1 is equal to 3. So this is new from yesterday. So we will have to work with that after we get our first steps done. So again, if we remember this is a cubic polynomial, that means it's third degree. If it's third degree, that means there has to be 3 roots. They give me 2 of them. They tell me there's a root at 2 and there is a root at 1 minus I. So the first thing I need to do is identify my third root. Right. Because it's a real coefficient polynomial, then that means if I have an imaginary root, then its conjugate must also be a root. So if 1 minus I is a root, then 1 plus I must be a root. Now we're working backwards. So we're basically going to multiply all these together. So that's x minus 2 times, when I move this over, that's x minus 1 plus I. And then here that's going to be x minus 1 minus I. And then we're going to distribute. So remember yesterday I told you, make sure you multiply the conjugates together first, because they help the imaginary units cancel. Okay, so let's go ahead and distribute here. That's going to be x squared minus x minus xi minus x plus 1 plus I plus xi minus I minus I squared. So because it's a 3 by 3, I should have 9 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. I've got them all. So let's go ahead and group our like terms together. So I've got minus xi plus xi. That cancels. I minus I. That cancels. So I'm left with x squared minus x is minus 2x. And then I have this I squared, which we can rewrite as negative 1. So I have minus a negative 1, which is plus 1. So then I have plus 1, which gives plus 2. So when I multiply those two complex roots together, I get x squared minus 2x plus 2. But I'm still left with this x minus 2 from out front. So I want to distribute that as well. So that's x cubed minus 2x squared plus 2x minus 2x squared plus 4x minus 4. We're going to group our like terms together. Minus 2x squared is minus 4x squared. 2x and 4x is 6x. So right here is my polynomial function. F of x equals x cubed minus 4x squared plus 6x minus 4. Now my new piece of information tells me that when I plug in 1 for x, I should get 3. Okay, so here is how we make sure that that happens. Because this is just a polynomial function. If you'll remember, back when we went through transformations of graphs, if I multiply all of this by a constant, then I am just stretching or compressing the graph. It does not change the intercepts. It does not change the roots. It only stretches or compresses the graph. So what I'm going to have to do is I'm going to have to multiply all of this by some value a. I don't know what a is yet, but I'm essentially stretching or compressing to make it be where when the x value is 1, I'm going to get a y value of 3. So I know what x and y need to be, so I plug those in, and my only unknown will be a. So that means f of x, which is just the y value, so I'm going to set that equal to 3, is equal to a times, now I'm looking for when the x value is 1, so I'm plugging in 1 here. 1 cubed minus 4 times 1 squared plus 6 times 1 minus 4. And now we're just going to simplify and solve for a. So 1 cubed is 1, 1 squared is 1 minus 4, plus 6 minus 4. That tells me 3 is equal to a times, that's going to be 7 minus 8, negative 1. And then when I solve for a, I get a is equal to negative 3. So that means I need to go back to my original here that I was multiplying by a, and I'm going to plug in a negative 3 for a. So I now have negative 3 times x cubed minus 4x squared plus 6x minus 4. So that means I ended up having to reflect the graph and then stretch the graph to make it have a y value of 3 when x was 1. Now then, we can distribute here to get our polynomial the way we're used to seeing it. That's negative 3x cubed plus 12x squared minus 18x plus 12. That's my polynomial function. Okay, so I want you to keep working on your own, but I'm going to kind of work behind you a little slowly in case some people get stuck. Maybe I can help you figure out where you're stuck at. So first thing we're doing, we're listing our roots. So we have roots at 1, negative 2, and 2i. I have to have a fourth root, and it's going to be the conjugate of my complex root. So I have another root at negative 2i. Then we're unsolving them and writing them as factors. Then distribute. And then we're getting rid of the I squared. Then distribute. Then we combine like terms. I have to make sure it fits my new restriction. F of negative 1 has to be 10. So that means I need f of x to be 10 when I plug in negative 1. So I'm going to multiply all of this by some a to make it fit that restriction. So I have negative 1 to the 4th plus negative 1 cubed plus 2 times negative 1 squared plus 4 times negative 1 minus 8. that's going to be 10 equals a times 1 minus 1 plus 2 minus 4 minus 8. So that's negative 12, negative 10, negative 10. So I get 10 was equal to a times negative 10. When I solve for a, I'm going to get a is equal to negative 1. So that means I go back to my original, my blue one here. I'm going to multiply all that by negative 1. So I have negative 1 times x to the 4th plus x to the 3rd plus 2x squared plus 4x minus 8. And then distribute negative x to the 4th minus x to the 3rd minus 2x squared minus 4x plus 8. Okay, this one here, I've got f of x equals x to the 4th minus x squared minus 20. I'm asked to find the roots. So I'm always going to begin by trying to factor. So is there a GCF here? There is not. Is this a special case that I can factor? It is not. So I can't do grouping. It's not difference of squares, difference of cubes, sum of cubes. But when I look at this, it is a trinomial. It's only 3 terms. Now it's not a quadratic, which is the kind of trinomials we're used to seeing, right? We're used to seeing something like x squared, bx, and c, like that. But it's close. It's x to the 4th, x squared, and then a constant. So think about if you took this and you doubled all of the powers. So this became 4th, 2nd, and then still a constant. Then this will still factor like a trinomial, even though it's x to the 4th instead of x squared. You just have to remember that when you write down your x terms. So we're still going to use all of our rules like we normally would. So I'm going to do, I could do a times c, which is 20. What multiplies to be 20 added or subtracted is negative 1. Negative 5 and positive 4. So I now have x to the 4th minus 5x squared plus 4x squared minus 20. So again, the only thing that's changed is the powers of the exponents. Now if I group, I'm looking for a GCF. I've got x squared, which leaves me with x squared minus 5. Over here I have positive 4, which leaves me with x squared minus 5. So my parentheses match. That means grouping worked. So this factors to be x squared plus 4 times x squared minus 5. Now, will either one of these factor? Not pretty. Not prettily. I don't know if that's a word. They don't factor great. So, because I have two things multiplied together, this is my factored form. Now, to solve it, to find the roots, I can set each one of those factors equal to 0. That's going to give me x squared equals negative 4. If I take a square root of both sides, I get x equals plus or minus. To get rid of the negative, I bring out an I. Square root of 4 is 2. So I have positive 2i and I have negative 2i. Then on the other side, I'm going to add 5. Take a square root. That tells me x equals plus or minus, and then radical 5 does not simplify. So right here are my 4 roots. 2i, negative 2i, radical 5, and negative radical 5. So again, hopefully you're working this. I'm going to go ahead and start behind you. So this follows the pattern, x to the fourth, x to the second, and constant. A times c is 3. So I have 1 and 3 to rewrite this as. So I have x to the fourth minus 3x squared plus 1x squared minus 3. That's how I'm rewriting that. And then group. And 1 is the GCF there. So grouping works because the parentheses match. So I have what's in front of the parentheses times what's inside the parentheses. Then I have to check, can I factor either one of these? I cannot. So this is the factored form. Okay, then next, I'm going to solve them to find the 4 roots. So I have x squared plus 1 equals 0, and x squared minus 3 equals 0. This says x squared equals negative 1. I'm going to take a square root. It tells me x equals plus or minus I. Square root of negative 1 is I. Then over here, I add 3 to both sides. Then I take a square root. Tells me x equals plus or minus radical 3. So right here are my 4 roots. I, radical 3, negative radical 3. So I'm having to find all the zeros, all of the roots of f of x equals x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. All right, if that was the last statement that I had was this, then I would say, is there a GCF? No. Is it a special case? No. Can I factor by grouping? No. So then if this is all that it said, then I would have to use synthetic to start guessing some possible roots. Okay, now in this one, it's not terrible because my leading coefficient is 1, right? But if you think about all the possible roots that we would have to try in synthetic, what are the factors of 60? Well, you've got 1 times 60. You've got 2 times 30. You've got 3 times 20. You've got 4 times 15. You've got 5 times 12. You've got 6 times 10. That's it. And so I'd have to try plus or minus all of those. So that's 1, 2, 3, 4, 5. That's 24 different things to try. Okay? So that could take a lot of time. If the only one that worked was way down here and it was like negative 20. Right? I mean, that would be really aggravating. Also, we're going to look at some later that are even uglier. Like, can you imagine if this was a 12 up here? Then you have to put all of these over 1, 2, 3, 4, 6, and 12. So now then my 24 possibilities just got multiplied by 6. 24 times 6, 144 possible synthetic things to try. Awful. Okay? Don't want any part of that. So, they give us a little hint. Now the little hint is going to seem like it's making it harder, but it's really simplifying all of the things we would have to try in synthetic. So it tells us 1 plus 3i is a root. So if you'll remember before, they would tell us something like, you check and see if 4 is a root. Well, if 4 is a root, then what did we do? We did synthetic of 4, and we simplified it. We had a new depressed polynomial. Well, the problem here is, they give me 1 plus 3i is my known root. Well, what can I just put in my little synthetic box? Well, nothing, because this is imaginary, that won't even work. But what we can do, because 1 plus 3i is a root, that means we also know that 1 minus 3i is a root, because this is a real coefficient polynomial. Every number I have is real. There are no imaginary parts. So if we have one complex root, then that means that its conjugate must be a complex root. Now I'm going to work backwards with these two and find a lower valued polynomial that I know is a factor. So I've got x minus 1 minus 3i equals 0. And I'm going to multiply that by x minus 1 plus 3i equals 0. Then we're going to distribute. So this is x squared minus x plus 3xi minus x plus 1 minus 3i minus 3xi plus 3i minus 9i squared. Okay, like terms. 3xi minus 3xi cancels. Negative 3i plus 3i cancels. Then I have x squared. I have minus x, that is minus 2x. And then deal with that I squared. I squared is the same thing as negative 1. So that means that's a positive 9. So I have a 1 and a positive 9, which combines to be 10. Okay, so what have I learned? I have learned that this is a factor. So that means I can rewrite this polynomial as this times whatever is left in parentheses. Okay, the problem is, can you look and say, well, if I factor this out from here, what's left? Well, no, we can't just look and see that one. That's not one that we can just identify. So to find the new polynomial, we have to do long division. So my original polynomial is x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. And I'm going to have to divide by the factor that I know works. So if I did this correctly, if this is indeed a factor, then I will get a remainder of 0. If I don't get a remainder of 0, then this was not a factor. Right? Think back to synthetic. How do we know if it works? If the remainder was 0. Well, here I'm telling you, this is a factor. How do I guarantee this is a factor? I should get a remainder of 0 in the end. Okay, so I'm writing that down. X squared minus 2x plus 10. So again, we haven't done long division with a trinomial out here yet, but it's still the same process. This is my leading term, x squared. I want to make it match the leading term, x to the 4th. So what do I need to multiply x squared by to make it become x to the 4th? I need to multiply by x squared. Then I have to distribute this x squared to all the terms. X squared times x squared is x to the 4th. They match, so I'm doing it correct. X squared times negative 2x, that is negative 2x cubed. X squared times 10, that is a positive 10x squared. Oh no. Okay? And then what happens in long division? We subtract, which means I'm changing all of these signs. So my x to the 4th cancel. Negative 3x cubed plus 2x cubed is negative 1x cubed. 6x squared minus 10x squared is negative 4x squared. Then I'm going to bring down my other two terms, plus 2x minus 60. Okay? Now I have an x squared, and I want to make it match negative x cubed. So what do I need to multiply by? Negative x. So I'm multiplying everything here by negative x. Negative x times x squared is negative x cubed. They match, so I've done my job. Negative x times negative 2x is positive 2x squared. Negative x times 10 is negative 10x. And now then I'm going to change all the signs. This becomes a positive, negative, positive. This cancels. Negative 4x squared minus 2x squared is negative 6x squared. 2x plus 10x is 12x, and I bring down the negative 60. Okay, now I have an x squared, and I want it to become negative 6x squared. So what do I need to multiply by? Negative 6, because I want it to match. So I'm going to multiply by negative 6. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 2x is positive, positive 12x. And then negative 6 times 10 is negative 60. And then what do? I'm going to change all these signs. So this cancels, cancels, cancels. Remainder 0, which is what I said was going to happen because it is a factor. So that means my big, ugly, original polynomial can be written as, what did I divide by? I divided by x squared minus 2x plus 10 times what I got as an answer, x squared minus x minus 6. So again, what did this save me the process of? I didn't have to try all those numbers in synthetic. It still takes a while, right? But there's no trial and error. And when the cases that you have 150, 200 things to try, this is a much better option. So now, will this factor again? Okay, well I know that this parenthesis will not factor again because I already know the two roots it gives me. It's going to give me 1 plus 3i and 1 minus 3i. Right, that's how I designed it, was with those two roots in mind. So I've already found 2. That parenthesis will not factor anymore because it gives imaginary roots. Now what about the other one? Can I factor the one underlined in blue? Yes, I can. That factors to be x minus 3 times x plus 2. So now this is my factored form. If it asks for the factored form, I've got it. Boom. If it asks me for all the zeros, then I need to solve. Again, the one in black, it gives zeros of 1 plus 3i and 1 minus 3i. Then right here in blue, if I solve, I get 3 and negative 2. So those are my 4 factors. So it turns out in this case, synthetic wouldn't have been too bad because 3 works and negative 2 works. Right, so we would have guessed those pretty quickly. But the problem you're fixing to get in your practice problem, the other roots you get are ugly. And there's no way you'd have guessed them. Or you wouldn't have guessed them quick. Right? You'd have guessed them towards the end. So again, this takes out guesswork, but it still takes a long time. So negative 4i must also be a root, right? That's the first thing that we know. So that means my factors are x minus 4i times x plus 4i. I can distribute to get a factor without any imaginary numbers. So it's going to give me x squared plus 4xi minus 4xi minus 16i squared, which I can write as plus 16. Right, because I squared is negative 1. Negative 16 times negative 1 is positive 16. So I now know a factor. I know x squared plus 16 is a factor. So I can do long division of that factor. So I've got 3x cubed minus 2x squared plus 48x minus 32. And I'm going to be dividing by that factor, x squared plus 16. So again, I have an x squared. I want to make it 3x cubed. X squared times what is 3x cubed? 3x. 3x times x squared is 3x cubed. 3x times 16 is 48x. So again, make sure you line it up properly, right? So it has to match up with the x term, not with the x to the second. That would be the trick in this problem. Then we're going to subtract. So this cancels and this cancels. That leaves me with negative 2x squared minus 32. I'm going to bring those down. Now I have an x squared, and I want it to be negative 2x squared. So I'm going to multiply by negative 2. Negative 2 times x squared is negative 2x squared. Negative 2 times 16 is negative 32. And then we change the signs. Those cancel. So again, that means it was a factor because I got a 0 remainder. So in factored form, this is x squared plus 16 times 3x minus 2. So this is my factored form. And then if it asks me for the zeros, for the roots are 4i and negative 4i. That's what the first parenthesis gives me. And then in the second parentheses, I would get 3x equals 2, which means x equals 2/3. So you see this time, your synthetic wouldn't have worked unless you put 2/3 up there in the little box. I mean, how long is it going to take you before you pick 2/3? A while. You're going to go through all the real numbers before you do any fractions. So in this case, it saved us a tremendous amount of time.